We are Dan and Ben from Bishop Fox. We are penetration testers. We spend most of our days breaking into things like web applications, networks, occasionally cooler things like safes. Like you, we've been hearing a whole lot about this AI business lately.
Yeah, I'm sure you've heard in the news. Seems like every week there's a new article in the news about how AI is going to start driving our trucks and cars on the roads. It's going to start flying our drones, and it's going to basically take all of our jobs. So as pen testers, we were interested in how we could use this technology and these tools to maybe do some offensive security stuff. We've heard a lot about defensive security applications for machine learning. There's things like firewalls out there that can do anomalous traffic detection and those kinds of things. But there weren't too many offensive tools, and so we really wanted to explore that space. And this talk is basically going to be about the intersection between AI, programming, and hacking. So
to give you a concrete example of this, we built a tool called DeepHack that breaks into the backend database of a web application using nothing but machine learning. So the scenario here, just in order to better understand what you're about to see, is an attacker taking an attack over the internet, over this a bank website, just say, that has a backend SQL database that has a what's called a Boolean-based blind SQL injection. So just in case you're not familiar with how that works, it's something like being able to ask 20 questions with a backend database. So you can do something like ask, hey, is like the user's first name starting with an F? And it'll say no. And it's like, does it start with a D? And you say no. You ask the question, does it start with a B? And you say yes. Okay. And so you can enumerate the entire database based off of this sort of thing. And there are tools that do this sort of thing, but none quite like how we did it. So in the demo you're about to see, this is all just taking place on one computer, my laptop, importantly here, the tool doesn't have any, say, insider information about the backend database, nor does it have any runtime information about like the web server itself.
Right, it's taking the perspective of an attacker on the public internet. This is just one of us,
Yeah, completely black box. So, demo. So what you're seeing right here, I'm going to just pause this for a moment here, is this sweet visualization. Hopefully you can read some of the text that we made that has on the bottom part are the requests that are being made out to the remote server. So you can see that it's querying the database character by character, asking for information from it. And up on the top there are like the discovered strings, basically. That's the information that it's received out from the remote endpoint. And you can see in a couple of cases there it starts to kind of freak out a little bit, and that's not what you would expect it to be doing. We're actually going to come back to that a little bit and explain exactly why the tool kind of doesn't always work exactly how you'd expect it to. And it can continue on this process, brute forcing character by character, stealing information out of the database until it has basically the entire thing. So a couple of like important pieces here is that our tool was never like programmed by us. Like we never programmed DeepHack. It learned how to do all of this, and that's going to be pretty important going forward, both for pen testing like tools and hackers in general.
Yeah, if you look through the code base, there is no SQL string that says select count from table. There is no hard-coded SQL logic. It's all just using artificial intelligence to kind of understand how that works.
Yeah, so we might say it has no tricks up our sleeve. We'll be releasing the source code to all of this stuff immediately following the conference, and you'll be able to see for yourself that it's about like 200 lines of Python. It's not some massive piece of new technology that had like never been discovered before. We don't have any major breakthroughs in machine learning. This is basically taking existing machine learning methodology and state of art and applying it to the world of hacking. Notably, like Ben said, there aren't anything like any SQL strings, there aren't any SQL structures, any information about web applications or databases at all inside of the underlying source code, the thing that actually is running this. The entire concept of brute forcing things character by character, the entire concept of what databases are and information behind that are all things that the machine has to learn. It has to discover that on its own. And importantly, also along the lines of no tricks up our sleeve here, is that this might seem sort of magical to you at this point, and that's almost on purpose. Imagine this whole presentation like a magic trick where we reveal how we did it at the end. Where this might seem kind of special and scary to you. If it's magic, then it's black magic, which is to say it's the kind that hacks into stuff. But I think by the end of this, hopefully you'll find that not only is this quite approachable, but in fact, in terms of machine learning, rather pedestrian. If there are any data scientists in the audience, I think they might find themselves like they could have done that themselves. And hopefully that's, in fact, what you come taking away from this.
Yeah, so our program differs a little bit from a regular program in a couple of really important ways. In a regular program, you write some source code, which is just going to be, in English, and you're going to basically be compiling it down to a binary, which is, machine instructions. It's the thing your computer is actually going to run, and those machine instructions are going to perform an action based on what you programmed into it. And there's a relationship between the source code and the action you eventually take. There's kind of this one-to-one mapping. So if you have enough time, you can sit there and reverse engineer any action your program has taken back to a line of source code. It's a very, very deterministic path back to what actually decided on that action. An AI program differs slightly in that there is still binary and there's still a program that's being written, but it takes in data and runs it through what's called a model, and the model is what kind of decides an action. So you're not going to be programming, conditional logic in there. If we're in state A, then we're going to take action A. Else, we're going to take action B. Right? There isn't so much of that, and the model will actually decide an action based on probability and just what data it has seen in the past. And that's kind of where the learning kicks in. It can use this data that you supply it with to kind of learn what has happened in the past and decide what actions it's going to take in the future. So there's it's not necessarily as deterministic as a regular program. It can be kind of difficult to actually ask, why did this program make the decision it did? Why did it decide to select star, or why did it decide to drop my database instead of inject and steal all the data from it? It's one of the fundamental differences.
Yeah, so we're going to be talking quite a bit about the model going forward, and that's an important piece to take away here. That's the thing that does all the smarts in your program as opposed to the code that you actually write.
Yeah, it's when I was learning how to do this stuff, I know a little bit of math, but I'm not a heavy math background, so I kind of had to take a different mindset to the programming, and I kind of consider it a different paradigm. You kind of have to formulate your problem a little bit differently, kind of how functional programming is a little bit different than object-oriented programming or imperative programming. It's kind of like a different paradigm. You definitely have to think about it slightly differently.
I described machine learning and artificial intelligence as a magic trick earlier, and if it's magic, then let's try to demystify that a little bit by learning a little bit how this works. Then maybe you won't be quite so scared of it once you discover exactly how this works. There was this fantastic cartoon I wish I could have put on here, but the text was too small to read, where like the Scooby-Doo gang go and just like pull the wig off of some sort of a monster that's like, oh no, machine learning, and it pulls the mask off. It's stochastic gradient descent. It was you all along. So yeah, something along those lines. I definitely get a universal sense of fear from people that I talk to this about, even my own mother. Where I described, she knows I do a bunch of like research projects and things like that, and not all that long ago she was asking me like, what are you working on these days? And I said, making this like AI program that learns to hack into a computer, and she just goes, oh no. Like, why would you do that? That's how it starts. Like, for whatever it is, I don't even know. So if you and Elon Musk are concerned about the same sorts of things, then just keep watching. Don't worry about it. Machine learning. So suppose we want to solve a much simpler problem. We want to solve this maze right here. We want to make a robot that can go up and over and solve the maze and not fall into the lava, or, depending on how you look at it, angry red birds.
They're lava birds, really.
Yeah, a lot of birds, so it would hurt. Yeah. So behold the table. This is the most simple machine learning algorithm possible. Basically, you just have your robot take actions and record the reward that it gets. So for instance, it might take a step starting at the starting position here, take a step left, fall into the lava and go, damn, that's minus 50 points, where I don't know, it just arbitrarily knows that 50 points is what you get for falling into lava. And then it knows to not try that again, or at least it knows to try to explore some other state. So it might then try moving upward and get -1 and say, hey, that was a little bit better. And so now that it's in the next square, it can go try, turning right, fall into the lava again, god damn it, gets another minus 50 points. And then basically just continue on this entire process, exploring things that it hasn't explored before until it's found its way to the start and it can derive the optimal solution. And this is basically it. This is machine learning. You just keep on trying things, you record what you found until you find a good way to the exit. There's only one problem with this.
Yeah, the problem is when you want to do something that's a little more complicated, for example, maybe instead of solving a maze, we'll play a game of chess. The problem is chess is a little more complicated than our maze, and it holds quite a bit more state. As you can see, there's about 10 to the 47 states in a game of chess. And there's only 16 pieces, or 16 pieces on each side. So there's going to be a lot of data to fit into our table. It's going to be very difficult, pretty much impossible to create a table, enumerate every single possible state, and decide what the best course of action is going to be. So one of the key points we're going to try to do is, or key things we're going to try to do is we're going to try to scale down the idea. We're still going to keep the idea of choosing random actions, figuring out if it was good or bad, and kind of recording that, but we're going to want to scale it down so we can explore state without having to store the entire game in our computer at the same time.
Yeah, we have pretty beefy computers, but it can't hold all that. So the main breakthrough here, the main idea behind actual machine learning as it happens in any normal sense, is that this table is basically just one of these, which is to say a function, a mathematical function, the sort that take numbers in and produce numbers out in a predictable way. And so what can we do with functions? We can approximate them. And so we have a following great little explanation of kind of how function approximation works without getting into some of the more nitty-gritty details. I suspect some data scientists that are in the room might be groaning to themselves. But actually, by the way, data scientists is sort of like what the AI community has decided to call themselves. It's a really terrible name. They're neither scientists nor have anything to do with data, really. If anything, they're data engineers. Come on, let's be straight. Yeah. And if anything, it's it should be like AI engineers. Get your shit together, AI researchers. So this is usually in the point of these sorts of conversations where things get really mathy, and mathematicians break out scary language like linear regression and convolutional transposition that scare away all the norms. But you don't actually need to know any of this. The frameworks are actually really helpful today, where you can write an AI programming without knowing a lick of any of this, which is the way the rest of computers work. You don't actually need to know anything of Shannon and entropy to write a goddamn Python program, right? You can use a crypto library without knowing any about RSA. And so the same is true just finally, recently, within AI frameworks. That's kind of why this has been taking off, because it's no longer something that MIT does in their for spare time. This is something that you actually can do today in a reasonably short amount of time.
Yeah, so function approximation. Basically, we're going to be trying to guess what the function that drew this line on this graph is going to be. So the easiest way to start with that is to draw the worst function approximation possible, which is just a straight line. This essentially represents your first sample. You have one data point. You're going to take one action. This is the first one. It's obviously going to be pretty terrible, but the great thing is you're basically going to just take another sample, and you're going to take another sample, and each time you're going to plot your data on your graph, and you're just going to keep on sampling until you kind of start getting close to your function. It's really hard to get perfect, especially when you're in the real world and you're trying to model something that's really complex, but you can get really close. And this idea of taking a random action or taking a smart action and seeing what happens, plotting it on your graph, and just repeating this process of sampling over and over again is kind of the fundamental thing you're going to be doing when you're building your AI program.
And more fundamentally, this is almost the very definition of learning, isn't it? What you're doing is you're taking in information, you're changing your model of the world on the basis of it, and then changing your behavior based off of the new things that you've seen, iteratively getting closer and closer towards the behavior that you'd like. Like I just described learning in a nutshell, right? This is just a mathematical way of representing that concept of learning. So however we try to do AI and machine learning in the future, it probably will take some form of function approximation.
Yeah, so there's kind of three things you want to think about when you start saying, well, okay, well, how do I, approximating functions, it sounds kind of complicated. How do I actually start, writing code? How do I start getting into this? You want to think about three things for your program. There's basically your input, which is going to be your environment. It's essentially everything your AI program knows about the world. I'm going to go into the next slide. We're going to talk about chess a little bit. It's going to be, everything your AI program knows, and it's the only thing it really sees. So you're going to want to try to formulate your inputs to, not present too much data, but also just present enough of the world to be able to make smart decisions about it. You're also going to have a reward. So when you take an action, it's either going to do something good, do something bad, or maybe do something kind of good or bad, depending on what your problem is. And then you're going to have your output, and that's going to be essentially what action you're going to take. So if you want to go then, if we're going to have a real concrete example here for our game of chess, our input would be the piece positions of all the pieces on the board. So you could put those in an array and just kind of just have be the entire state of the program. Your rewards are going to be if you move a piece, what happened, right? If you take a piece, you're going to be gaining some reward. You're going to get that carrot, right? The reward is your carrot on a stick, carrot or stick. So if you capture a piece, you're going to be getting some reward, and if you lose a piece, you're going to be gaining some negative reward, or losing some negative reward. And if you move perhaps without actually taking a piece, it might be just a slight negative reward because you didn't really accomplish anything, but you also didn't lose anything too great either, just some time. And then, like I said, your output is essentially going to be the action that you're going to take for your game. So
and that's really about it. If you're wondering in the audience right now, or at home, Gerben, if you can try to make some sort of a program that can take advantage of machine learning, try to think about it in terms of these three things. But input, which is say, what are the things that my program needs to see in the universe? Output, what are the actions that it should be taking? And then rewards, how does it know when it did something good, or how does it know when it did something bad? If you can think of your problem effectively in terms of those three things, then you can make a machine learning program that will solve your problem. So getting back to our example, getting back to DeepHack specifically, it works a little bit like this. This might seem at first like an unintuitive way of formulating the problem, but it's actually pretty standard construction in terms of text generation. So the input here to the system is an incomplete query string. It's a partial string of text that it's generating. And the output, the thing that it needs to decide, the thing that it wants to figure out, is what is the next character in this sequence. So if you're looking at our example here, it says select star fro, and then even in the audience here, you could probably think, well, M makes sense, right? Especially if we're talking about SQL, then it should be select star from. And then what you do is you take that M, you stick it onto the end of the query string, and then you just repeat this process iteratively. And in terms of rewards, how does it know whether it did something right or whether it did something wrong is again based off of the output from the remote server. So all we have information about are the Boolean-based responses from the web server. So did this give us a 200 or did it give us a 500? Which to say, like, is that data correct or is it incorrect? And so entirely from that basis, we can figure out whether the string is present in the database or not, or whether this is something that we want or whether it isn't. So as a good tangible example of this, you can imagine like we do this in English all the time. In fact, you do this in your cell phone all the time. And so we're going to play a little game here. I want you to bust out with your cell phones right now and open up your text message app. Because your cell phones do this currently right now pretty well. So you're going to open up a text message app, whatever that happens to be, probably Signal because we're hackers, right? You're going to go to somebody that you really like, or maybe you really hate, and just type something in. Say like, I'm at DEF CON space, and then it's going to give you a series of recommendations, which is your like machine learning assistant in your phone telling you what it thinks should come next. Just go ahead and press one of the buttons. Pick left, middle, or right, right? And then just keep on pressing the button, and then just keep on pressing the button. And you'll notice that it starts to generate some pretty hilarious strings. Oh yeah, my phone is going awesome. I'm going to read you this in just a moment. And the trick here is you have to press send. That's part of the rules of the game. You agreed to it.
Yeah.
I'm pressing send. I'm at DEF CON. This is the first time, which is not, I have been every right to be mad at me for not being able to that day for last weekend. And this is getting serious. And wanted to see if I could get a copy of the receipt for that. It was a weird night in Vegas last night, apparently. Yeah. I'm married. Well, I'll get back to you on that. Your receipts. Yeah. And I'm hitting send. So this is basically like what DeepHack is doing, right? So it's taking the information from the string it has seen before, as well as in your cell phone case, what has been the history of things you've sent in the past, and tries to figure out a good suggestion for that. And then that's really all there is to it. So you can imagine here, if you have a sentence like a lot of foo, then the machine will try to create a good suggestion for what letter should come next. Some good examples might be D, like a lot of food, or maybe a lot of foot. Maybe there's a lot of football you've been watching or something like that, or maybe even foosball. And so strictly speaking, the machine doesn't pick the next character. Actually what it does is produce a probability distribution across all letters, and so it might give D a very high probability, T a very low probability. And so the entire nature of the program is probabilistic. And that leads us to why DeepHack sometimes wigs out and does stupid shit. Because if you start out your sentence in the text message game with something nonsensical, or if you just kind of like pick something random, then it goes off the rails quickly. So if the very first couple of words have nothing to do with SQL and it just starts talking about like food, then the DeepHack has no idea how to recover from that and basically just shits the bed.
Yeah, so some of the things to keep in mind, some of the things we ran into when we were trying to write our program were having good data is really key. You want to have good labeled data to feed into your model to have a good basis. Like Dan was saying, you could pretty much throw DeepHack at a web server with no training, and it would just barf all over the place. It would be really good at generating random text, and eventually you might run into some SQL queries, like maybe some simple ones, and 1 = 1 or whatever, that would actually work, and it would be, a light bulb would go off in it. But that would take a really long time, and we don't have a lot of time on engagements. So you want to basically train your model with labeled data that you've collected over time, so your model can learn a little bit about the problem you're trying to solve before you just unleash it onto the world. So that's what bootstrapping your model with experiences is. That's kind of what it's called. You're going to give your model some experiences and try to teach it, kind of like a small child, perhaps. You're going to
Yeah, making a machine learning program is a bit like having a child and teaching it to solve your problem instead of you having to do it yourself. It can be a rather frustrating experience and get messy at times.
Yeah, you have this indirect control over your program. Like, could you please maybe do that? That would be really great if you could start hacking. That'd be great. Yeah,
so it turns out that computers don't necessarily have to be taking action themselves in order to learn from it, right? You can give it experiences from other machines or things that it had seen in the past to try to get it bootstrapped into better behavior. Like Ben had said, if you just start DeepHack from scratch, it just produces garbage. It doesn't do much of anything else. And if you give it an infinite amount of time, it'll eventually come up with a good SQL string. But that's not really good enough, right? So getting a good sample of training data is usually the difference between a solvable problem and one that isn't. So again, in your problem, if you're thinking, I wonder if I can solve X with machine learning, try to think about how can I get a metric shit ton of data on my problem that's labeled data. And it has to be labeled data, which is to say that you have to know ahead of time what it is and what it isn't. So for example, if you're making a computer program that tells the difference between a hot dog and not a hot dog, then it's not enough to have lots and lots of pictures of hot dogs. You have to have lots and lots of pictures of hot dogs and to know ahead of time that they are hot dogs. Because you have to tell the program that it's what it is, right? It's not going to just figure that out on its own. Or you can get your users to do it for you. This is a picture of reCAPTCHA.
Yeah, and I'm sure you've filled out a lot of reCAPTCHAs in your day, and you're basically just feeding a machine learning algorithm, and you're helping train up, a really impressive algorithm that can decide if you're a bot or not. And it's great because you're just kind of renting out your brain power and helping the greater good of the internet, pretty much, with that. So yeah, if you can coerce or convince your users to perhaps help you out, train your models, and label some data for you, all the better. So,
Google's remarkably open about the reCAPTCHA thing too. I thought this was really surreptitious, but now it says it like right on their homepage. They're like, "You're feeding our machine learning algorithm, bro." Like that's what's happening here. Yeah. Curiously, they actually do it really cleverly. In this picture here, that has a picture of a cat and says, "Select all the images that match this one below." And my brain immediately went to cats, and so I was like, "Well, these ones are cats and these ones aren't." I was showing this to my wife ahead of this time, and she said, well, everything except for the bottom left one. And I was like, what? What are you talking about? And she said, well, that's the only one that's not an animal. I was like, oh, that's actually really clever. And then if you read the prompt, it doesn't say pick all the ones that are cats. It just says pick all the ones that are similar to this below. And so that way they actually get a really big sample of results from things that are just similar for whatever that means to you. And so they can get an idea of what things are similar to human beings without actually telling you the categories for what those mean. So that's actually really clever.
Yeah, very smart.
So maybe at this point you're thinking, like, so what? So you made some computer program that hacks into a web applications database, like, they already have programs that do that? And that's true, but there's part of what makes DeepHack special, and part of what might make you want to make AI-based hacking tools in the past, is there's nothing actually in what we were talking about that's specific to the underlying database type. In fact, part of the entire thrust of this is that it's agnostic to the underlying database type, the structures and things like that. So in the previous example, we showed you exploiting a SQLite database because SQLite was easy. Here it is again using Postgres. And so in this case, you can notice that the database type is completely different. The query that it's making is totally different, but it works nonetheless. And this is the reason that AI is going to take off. This is the reason that this is going to be big, and the reason that basically every major pen testing tool, certainly in 2018, but maybe even in 2017, is going to start to add this. You're going to see Web Inspect and Burp, and basically everybody else adding machine learning to augment existing tooling, because it can take care of this kind of fuzzy logic for you. You don't have to rewrite your tool to do any of this. And in fact, the SQLite and PostgreSQL's attacks here that we just showed had exactly 0 lines of code changed in them. So without changing a single line of code, you can train your tool to do a completely different job, as in completely different details, not a completely different job.
Yeah, and that generalized kind of you kind of have this infinitely flexible general function, and that's going to be super valuable for tools going forward, not just injection attacks, but a lot of other attacks. So
yeah, that was demonstration. So some lessons learned. It turns out that quality training data is really important. We originally had a couple of ideas about how we were going to gather training data. One of our first ideas was to just scrape the internet for SQL strings, and this actually works fairly well. You can just find projects open source on GitHub that have SQL structures, and a tool can look at that and learn what SQL is, what sort of structures of it are, what are the kind of terms that it has. But what it doesn't have a whole lot of our injection strings specifically, so we can teach our bot to speak SQL, but it doesn't know how to inject. And so in order to try to bridge that gap, we thought, well, hey, maybe we can just use SQL Map. Since SQL Map is another tool that does basically this. It turns out that SQL Map generates strings that are just really fucking complicated. It's in this vein of tools that we refer to as the worst best tools, in that it's clearly the best tool at doing what it does. It works really well. We use it on engagements, but at the same time, it's just the worst. And the strings that it generates are just really complicated. The model had a really hard time picking up on it because it does things like a binary search algorithm as opposed to just character by character.
Yeah, it was really hard for the model to derive that binary search from SQL map. So we had to simplify it down, and we basically made bad SQL map, which does regular Boolean search, Boolean blind injection. It doesn't use binary search. It just kind of brute forces character by character. So training data, super important to get. Scraping the internet, becoming Google is pretty hard. They do a pretty good job of that. So you want to try to get really good training data, and also you want to be incredibly careful about what you're rewarding. It seems like kind of common sense, but it can really sneak up on you in really interesting ways. One of our big problems that we ran into, well, not like a big problem, but one of the funny things that kind of happened was we didn't incentivize characters we had already found. And we thought that, oh, well, we're rewarding, characters we found. We'll try this. We ran it for, a long time. And then we just found out our database or our tool is really good at just brute forcing the same character over and over again. So we knew the table started with A really well. We had that definitely locked down.
Yeah, it was the bird getting a piece of seed every time it found a letter, right? So it got A. We gave it a reward. Got A again. It kept on giving a reward. Motherfucker kept on finding A. So we're like, oh, okay, you will get more of whatever it is that you reward. And so you have to be really careful about that. You might think that you've described the problem accurately when, in fact, your computer has found some clever loophole in your own rules in order to just get an arbitrary amount of reward.
Yeah, and another thing we learned is get a GPU, or better yet, get a lot of them. We had a significant speed up from GPUs, and there's a lot of great companies out there that are selling cheap GPUs, and you can just rent them on the cloud. It's like super easy, spin up, and it really helps. We had like something like a 20 times speed up when we were training our models. So it's really easy to kind of get started with this stuff, and then once you kind of get an idea for something you want to try, definitely get a GPU. It'll speed up your debug time. That was one of the frustrating things kind of early. You have to train up your model every time you make a change, so you want to try to make good changes, and then an hour later you can find out if it was actually a good idea or not. So
you
GPUs,
thought compile times were bad.
Yeah, it's like going back, massive C++. So yeah, the getting GPUs super helpful. More the better. More the better.
So some other considerations here about neural networks and AI and hacking in general. Neural networks have this kind of inherent proprietariness to them in that there's no really good way to debug them or to know what they're doing, like even really in principle. Your code, your logic, the thing that determines what your program is doing is a shape. It's a literal geometric shape, not figuratively. It's like actually it's a function, right, that has a shape. And so if you try to ask the question like, hey, why did my machine learning car just like run over a dog? The answer is, fuck you, that's why. Like it did it because that's what it did it. Like there's no good reason for it. It just followed the shape that it thought it was supposed to follow. And so this is a problem both for, like debugging purposes. In a former life, I was actually responsible for writing test cases for flight software. And we had extremely strict what are called code coverage requirements, which is to say that I had to write test cases that hit every single line of code in the entire suite of programs in order to test that the whole thing wasn't just going to fall out of the sky. And we care about that sort of thing in terms of reliability of critical safety environments. And I don't even know what does that even look like for an AI program? Like you can make a self-driving car that will on average be safer than a human being because you can make a chess playing robot or a Go playing robot that's better than people. But can you have any strong assurances that it just won't go haywire? Like not really. Yeah. It doesn't even, I don't even know what that looks like in principle.
Yeah, and who's responsible when it does go haywire, So.
Aside from the entire liability issues.
Right.
Also, if you're the sort of person who cares about free and open source software, this should also sort of worry you in that the program behavior is not debuggable. It's not reversible to any original form. Even if you're given the entire set of data that the person trained and the source code to it, you can't combine them to create the same program. It's just stochastic, which is fancy math terms for random. Mm-hmm. And so that's also an inherent problem. So what does it even mean to have an open source AI program? We should start having a conversation about that.
Yeah, the big cloud providers, Google, Facebook, all those big companies that do a lot of this kind of research, they will happily rent you out their spare CPUs cycles, and they will happily, rent you out your GPUs, but they will never ever rent out their models and their massive collections of data to you. That's kind of the secret sauce, right? So if all that is hidden, you're kind of at a disadvantage if you want to get started with this stuff. Big hill to climb.
Yeah, in a way that's not present with ordinary programs. There's a reason you see all the major breakthroughs and this sort of thing coming from large companies that just coincidentally happen to have access to everyone's data, because you need vast amounts of data in order to make these sorts of programs happen. If you want to tell the difference between a stop sign and a dog, then you really need to have lots and lots of pictures of stop signs and dogs. And if you, the average programmer, want to make a program that does that, you just don't have that data, and the people who do aren't sharing. And moreover, like programs, AI writing an AI program is like incredibly fun. It's actually really rewarding and a lot easier than you probably think it is. There are some great libraries out there like TensorFlow or actually Keras, which wraps that up into a very easy sort of higher level library. But at the same time, it could be a really frustrating experience because every once in a while the program will just do something that you didn't think you told it to do, or it'll just like start going haywire and you have no idea why. And you try to ask the question like, why did it do that? Is it because you didn't train it enough? Like that can always be a problem. Did you train it too much? Because that's a thing too. Like it's just kind of really hard. There's also really fun problems like what can best be described as
Overfitting?
Yeah, you can forfeit data basically from the data to try to make it better. Basically, is what I'm getting at. Yeah. So some future work here. If you're like looking at making some data that or some programs that will exploit various things. I know we have some ideas about what we want to take care of coming here in the near future, or things that we're actually already working on. And here are some like good crunchy problems. As a good rule of thumb, there's a really prominent researcher named Andrew Wen who is responsible for a bunch of this stuff. Says a good rule of thumb is like if a human expert can solve the problem in like a couple of seconds, then that's probably something that's eminently solvable by a machine learning algorithm right now. And so if you think back into all of the things that you do in terms of like your tasks as a pen tester or as a hacker or whatever, there's probably quite a bit in there that can be automated in terms of what is fuzzy logic that maybe you do as a human. That would be a really hard thing to make a computer that would do that.
Yeah, kind of hand program logic in there. So one thing that I'm really excited about is password brute forcing, because when you're trying to brute force some passwords, it starts with a word list, and then you kind of hand jam some rules to kind of mangle the word list. If you see the month of or the current season, you say, okay, well, I'll throw the end of the year, the current year on there, and maybe a bang at the end. Those kinds of rules are definitely just kind of things you've thought are a good idea, and they seem to fit a pattern from the data. Well, a machine learning algorithm would be really good at picking up on those patterns from password dumps that have been dumped, and could potentially generate rules for you automatically. And they might be better than the ones you can think of yourself. They might be able to see things and see patterns and have relationships that you wouldn't really be able to see.
Yeah, in fact, that's something that we frequently do on engagements when we are cracking passwords that we've dumped from whatever. We'll frequently get a little ways in, look at the passwords that we've already brute forced, and then try to kind of manually sift it for patterns. Like maybe the first character is always capital and the last letter is always a number, or perhaps it follows some like company pattern, or if you have an organization like everybody else's that expires passwords every quarter, then they tend to have things like spring 2016, fall 2017 as passwords. And so if you had a machine learning algorithm that could automatically pick up on these patterns, that would be a really good addition to existing password brute forcing methodology. In addition to that, we have things like an instrumented web app fuzzer, something that's given the internal structures from an instrumented Python web application, can see the internal data structures and logic, and can try to produce inputs that will exercise as much of that. Basically like AFL, if you're familiar with that, but basically potentially much smarter in that it uses a neural network, but also for a web application. That's a much larger set of sort of things to attack.
Yeah, and like I was saying before, there's a lot of hype about this kind of stuff. There's tons of media coverage about it. It's in Hollywood and all kinds of stuff. All these AI programs. But what it's actually kind of bad at is discovering like a new class of vulnerability, right? So it's not. AI isn't really going to, at least in the short term, it's not going to be able to discover new types of vulnerabilities. It's probably not going to be able to find some kind of new crazy injection flaw that we just don't know about. And a lot of that comes down to context, especially with security testing. Context is pretty key around some application behavior and functionality. Sometimes it's totally all right to be able to run remote commands on a machine because that's the tool's purpose. The machine learning algorithm doesn't know that, so it doesn't really have the context to decide what is a security risk and what is not.
Yes.
So,
suppose you make a request and a social security number comes back. Like, is that a bug? Is that intended behavior? It might actually be a legitimate website that's supposed to do that. How is the computer supposed to know whether it's a bug or not? This is kind of a more fundamental question about like what is a security bug, right? Reasonable people can disagree sometimes on this fact. And moreover, the computer is missing context. So imagine teaching a computer, or yourself in fact, learning a whole new language entirely on the basis of dictionaries. So you read a whole dictionary, you read a thesaurus, you can read all as much the structure and syntax of a particular language as you want, right? Say French. And then you go to France and try to talk to people and you be completely shit out of luck. Somebody's going to tell you some sort of idioms, say like, take a hike or something like that. And you have no idea what that means in context because the language is about more than just the words on paper or words as they're spoken. It's a part of culture. And so the same thing is true of security in general, that what is and is not a security problem often just depends. And so I suspect that machine learning algorithms are going to be quite bad at doing this sort of thing and quite good at automating tasks that used to be fuzzy logic that computers previously quite bad at. And I think that's a very large space in computer security that could be taken advantage of.
Yeah, unfortunately no Skynet right now. But yeah.
That's it. We have a couple minutes for questions if anybody wants them.